Welcome to The Explainer. Today, we're diving into the visual magic of complex functions. We're going to see how a simple equation can stretch, twist, and fold the very fabric of the mathematical plane, creating some absolutely stunning geometric transformations. So, let's start with a little puzzle. On the left, you've got an entire infinite half of the complex plane. And on the right, it's been perfectly squished into a simple, finite disk. I mean, how is that even possible? Well, this isn't some kind of mathematical party trick. It's a powerful transformation, a mapping that we can actually see and understand.
To get our heads around these incredible transformations, we need to think in two separate worlds. First, you've got the z-plane. That's our starting point, where our original shapes live. And then there's the w-plane. That's where the new, transformed images pop up after we apply a function. So here's the basic idea. We take any point z from the z-plane on the left, and we feed it into our function. The function does its thing, crunches the numbers, and spits out a new point, w, which we then plot in the w-plane on the right. And when you do that for every single point in a shape, you get a brand new, totally transformed version of it.
Okay, so how do we actually build these transformations? Well, we've got to start with the fundamentals. Let's look at two of the most basic types of mappings. You can think of them like geometric tools that let us play with the plane.
The linear transformation, this is our most basic tool. Multiplying by that a lets us rotate and scale the plane, spin it and zoom in or out. And adding b, that just slides the whole thing around. It's really just like using the transform tool in Photoshop. You can rotate, resize, and move an image, but the shape itself doesn't fundamentally change. Now, the inversion w equals 1 over z, this is where things get really wild. This transformation basically turns the entire complex plane inside out, with the unit circle acting as the mirror. It's like a geometric funhouse mirror, but it's one with very specific and, believe it or not, predictable rules. And here are those rules. Inversion maps circles to other circles and lines to other lines. Well, most of the time. The really cool part is that they can actually trade places. A circle that happens to pass right through the origin gets flattened into a perfectly straight line. And a line can get curled up into a brand new circle. It's amazing.
All right, let's level up. Now we're going to explore a much more sophisticated tool, one that builds a completely different kind of geometric fixture, the exponential function.
The geometry is hidden right there in the formula. For our input, z equals x plus iy, that real part, the x, ends up controlling how far our new point is from the origin. And the imaginary part, the y, it controls its angle. It just so beautifully separates our rectangular coordinates into polar ones. And this right here, this just brilliantly shows the core action of the exponential map. It takes that familiar rectangular grid of vertical and horizontal lines in the z-plane, and it wraps it into a polar grid in the w-plane, made of these perfect concentric circles and rays shooting out from the middle. It is a fundamental change in the geometry of the space. But here's a really strange quirk. Unlike the real exponential function we're all used to, the complex version is periodic. If you take any point z and you just shift it straight up by 2 pi I, you land on the exact same output in the w-plane. What this means is that infinite horizontal strips from the z-plane all get layered right on top of each other in the output. It's pretty wild. Okay, now for a function with a completely different personality, the square root function. And this one introduces a genuinely mind-bending concept into our mappings. So here's the core issue we run into. Every non-zero complex number actually has two square roots, right? The square roots of 4 are 2 and -2, and the square roots of -1 are I and -I. So if we put one number in, we get two numbers out. How on earth can we visualize a mapping like that? This formula, it tells us everything we need to know. That nth root r part means all the roots are the exact same distance from the origin. They all lie on a single circle. And the second part, the exponential, that tells us their angles. It takes the original angle, divides it by n, and then that little 2k pi term creates all the other roots, spacing them out perfectly and evenly around that circle. And the result is just stunning. The roots aren't scattered randomly at all. They form the corners of a perfectly symmetrical polygon. For the number 1, its 3 cubed roots form a perfect triangle, its 4 fourth roots form a square, and so on. It's a perfect example of the beautiful, beautiful geometry that's hidden inside the algebra. Now, to actually use this for our transformations, we need a predictable function. One input, one output. So we have to make a choice. We define what's called a branch of the function, like the principal root,
where we basically agree to always pick just one of the possible outputs. This is how we tame that multi-valued nature so we can actually use it for mapping.
All right, let's put our two star players, the exponential and the square root, side by side. This will really help us understand their totally different geometric characters and how they reshape the plane. So this table really sums up the key difference. The exponential function is single-valued and periodic. Its main geometric move is to wrap the plane around the origin over and over and over again. In contrast, the root function is multi-valued and it needs branches to work. Its action is to unwrap the plane, taking a full circle's worth of inputs and mapping them to just a half plane.
You see, these basic functions, translation, rotation, inversion, exponential, and roots, they're just the building blocks. They're like Lego bricks. And by combining them in sequence, we can create these incredibly intricate transformations, like the one we started with that maps an infinite plane to a finite disk. They are the fundamental tools for a kind of geometric engineering. So my question for you is, what other shapes could you create?